Hello. This presentation is on probability theory and exact inference in Bayesian networks. Let's begin by going over some important definitions before we go into the specifics of discrete probability. An experiment is a procedure that yields one of a given set of possible outcomes. The sample space of the experiment is the set of possible outcomes, and an event is a subset of the sample space. If S is a finite non-empty sample space of equally likely outcomes, and E is an event, that is, a subset of S, then the probability of E is the following equation. And when dealing with the probability of an event happening, the likelihood is between 0 and 1. A brief note on Pierre-Simon Laplace, who is considered to be the mathematician that completed the classical definition of probability. He was one of the founders of probability theory and made many contributions to mathematical statistics. In his book, Analytical Theory of Probability, he defined the probability of an event as the ratio of the number of favorable outcomes to the total number of outcomes of an experiment. Suppose that S is a set with n elements. The uniform distribution assigns the probability 1 over n to each element of S. When possible, outcomes are equally likely and there are a finite number of possible outcomes. This definition and Laplace's definition agree with each other. We can see this by supposing that there are n equally likely outcomes. Each possible outcome has probability of 1 over n because the sum of their probabilities is 1. We can use counting techniques to find the probability of events derived from other events. In general, to find the conditional probability of E given F, we use F as the sample space. For an outcome from E to occur, this outcome must also belong to the intersection of E and F. With this information, we can derive the following definition on the right as we see here. When discussing independent events, the occurrence of one of the events gives no information about the probability that the other events occur. For example, if a coin is flipped 3 times, we can ask the question, does knowing the first flip result in tails affect the probability that tails come up an odd number of times? This equality is valid for the events E and F because the conditional probability of E given F is 50% and E is 50%. Because of this, we can say that E and F are independent events. An experiment that can only have 2 outcomes for each performance of the experiment is called a Bernoulli trial, after mathematician James Bernoulli. In general, a possible outcome of a Bernoulli trial is called a success or a failure. If P is the probability of a success and Q is the probability of a failure, it follows that P plus Q equals 1. Bernoulli is best known for his work Ars Conjectandi, in which he describes results in probability theory and in enumeration and provides alternative proofs of the known results. Ars Conjectandi also includes the application of probability theory to games of chance and his introduction of the theorem known as the law of large numbers, which is defined here. A random variable is a function from the sample space of an experiment to the set of real numbers. That is, a random variable assigns a real number to each possible outcome. The idea behind Bayes' theorem is that we can arrive at a more realistic estimate that a particular event occurs. Suppose we know the probability that an event F occurs, but we have knowledge that an event E occurs. Then, the conditional probability that F occurs given that E occurs is a more realistic estimate than the probability that an event F occurs. A Bayesian network is a probabilistic graphical model that represents a set of variables and their conditional dependencies via a directed acyclic graph, also known as a DAG. These are best for taking an event that occurred and predicting the likelihood that any one of several possible known causes was the contributing factor. The following algorithm is from an artificial intelligence course at MIT and is an exact inference in Bayes' network. The enumeration algorithm is a simple, brute force way to compute the distribution of a variable in a Bayes network. The enumeration as function takes a variable and returns a distribution over said variable, given some evidence. It has to compute a distribution over the variable by looping through all of the possible values and computing the probability for each one. If no evidence is given, it is simply computing the probabilities for each possible value in the variable's domain. If evidence has been given, then the multiplication law of probability is used. The enumerate all function is a helper function which computes the probability of the evidence. Every time this function is called, we look at the next variable, y, from vars. It is either assigned an evidence to some value or y is not assigned, for which it has to sum over all possible values in y's domain. The variable elimination algorithm's goal is to compute probabilities and then compute the other terms that depend on them, and repeatedly simplify the expression until we have something that is in terms of only the variable we are looking for. This algorithm uses factors, which are conditional probability tables, except that the entries are not necessarily probabilities. They are essentially tables with one row for each possible combination of assignments of values to the variables. This as function, similarly to the previous as function, takes a variable and returns a distribution over it, given some evidence. It starts with initializing the list of factors. Then it sums out each variable from the list of factors. This process takes all the factors that depend on a given variable and replaces them with a single new factor that doesn't depend on that variable. At the end of the loop, all variables have been summed out except the query variable, so that the factors are multiplied together and normalized to get the distribution.